So welcome back. What we're going to do in the second half of today's course session is to work a little bit more with finite automata, understanding more formally than we've done so far what really is a finite automaton, because if you are a computer program who needs to operate with finite automata, you need to know precisely what is a finite automaton so that you can reject all the stuff that is not a finite automaton, and you can work with the stuff that is a finite automaton. Before we do that, let's work a little bit more with what we've been doing so far. So far we've been drawing states, an automata like the one that we have here on our drawing tool. And I haven't given any names for the states because, well, more often than not, we don't need to name them. But let me give you for once the boring, gory details as to why and how you can argue that this automaton accepts a given string. So let's, this is state S0, this is state S1, this is state S2. Let's just do pen for the time being, even though I like to be calligraphic. So the state S0 of the automaton is the start state. So how can we actually, if in doubt, check whether this automaton accepts the string 0, 0, 1? It should accept this string because it's in the language that we want this automaton to recognize. So how can we figure out that this string is really accepted? Well, the automaton starts computing from the initial state as 0. It starts reading its input, and the first thing that it reads is the 0. Where does it go by reading the 0? Well, we look at the graph that represents the behavior of the automaton. This graph tells us that we stay in state S0. Sort of, yeah, that's an S0. I need to warm up my hand and my writing skills. I love writing, but not on this thing. Okay, what next? We read another 0. That's the second one. And again, we stay in state S0. I'm getting slightly better now. Okay, now we got to read the next input symbol. It's a 1. And we follow the behavior of the automaton. We enter state S1. Now the automaton asks, are there any more input symbols? No, the empty string, the input string is finished. So how does the automaton determine whether it accepts or not the input string? It looks at the state that it has landed in, S1, and it asks, is it a happy state? Is it an accept state? The answer is yes, because there is a double circle there. And so the automaton says, yes, the input string you gave me is one that makes me happy. I accept it. And then you get a smiley. That was the question. Do we get a smiley? Yes, you get a smiley. You smile. The important thing is that you smile because you got it right. You did a good job. Fantastic. So can you give me the simplest finite automaton that accepts the empty language and it can process bit strings? So its input alphabet is 0, 1, the set 0, 1, but it should accept nothing. And I want you to use the KISS method. Give me the simplest automaton that can process bit strings and accepts none of them. That's what at home they say, that this is my behavior. I'm forever unhappy. Okay? Don't quote me on this, even though I'm live on YouTube. Okay, your colleague is saying, okay, we need a start state. The start state is unhappy, so it's not an accept state. And since we always want to be unhappy, the natural thing to do is to have a loop on that state for anything that we read. The start state is this one. It's the only state. Oh, no, no. So so the question is, shouldn't we have another state before this one? The answer is no. This incoming arrow here, which I perhaps made too long, indicates that this state is also the start state. In this case, that's sort of given because it's the only one. But let me be consistent. This says this is the only state and it's also the start state. Oh, you don't want to accept anything. Oh, okay, okay, okay. Your colleagues are saying, shouldn't we have the start state as a happy state, and then we go somewhere, no matter what we read, and from this somewhere we stay unhappy? Now, this would be my next question, actually. So thank you very much. Are these two automata accepting the same language? Or is there some string that one automaton accepts and the other one does not? Yep, your colleagues are saying they are not the same because this automaton here accepts the language that only contains the empty string, whereas this automaton here accepts the empty language. And these two are very different languages. One of them, the empty language, is the language that contains no string. The other one is a language that contains one string, the empty string. Okay? Remember, languages are like sets. When are two sets, in fact, they are sets, they're sets of strings. When are two sets equal? That's elementary school 101. No, sorry. Two sets of objects are equal. Two sets are equal if they contain the same elements. Okay, I know discrete maths 1 was a long time ago, sort of prehistory. It was in a different year as well. But anyway, you will meet lots of sets in this course too. So two sets are equal, and in your careers as well. Two sets are equal if they have the same elements. If you have a set with no elements and one with one element, they cannot be equal. Okay, so the empty set is like an empty backpack, whereas this set here is like a backpack that contains one string. The string is empty, but there is a string in there. There is life in that set, in that backpack, whereas there is no life here. Okay? So these are two different automata. This one only accepts the empty string. This one accepts nothing. No string at all. So far, so good? Excellent. So we are warmed up. And in fact, we've done this exercise here. That's why that would have been my next question. Okay, but now you might say, that's really groovy. So far, we've been drawing finite automaton. But you haven't told us what a finite automaton is. So we've just been drawing pictures. So if somebody tells you, okay, tell me, I've been drawing this thing. Is it a finite automaton? Well, you need a definition in order to be able to answer that question correctly. So what is a finite automaton? Formally. Now, I know this is going to be boring, but it's sort of necessary. So let's do it. A finite automaton, or better, a deterministic finite automaton, for the cognoscenti, that's DFA. So if you want to sound cool, you call it a DFA. Is a tuple. You know, lots of things are tuples in life and in computer science. It's a tuple that consists of 5 items of information. What is the first item of information? It's a collection of states of the automaton. That's the set of states that the automaton can be legally in. Second, every automaton, every deterministic finite automaton or every finite automaton is built to recognize a language and the language consists of strings over some alphabet. So the second item of information is a finite input alphabet. That's the alphabet consisting of the letters that we can use to write strings that we feed to the automata. So far, all the automata that we built are over the binary alphabet. So in that case, I would be the set 0, 1. There is always a single start state, which people always call S0 or Q0, depending on whether you like S or Q. And there is a set of final or accept states. These were the smiley states that we had before. This set should be a subset of the set of states of the automaton because they have to be states in the automaton. Now, so far, so good. That's the boring part. But where are the edges that we were drawing on this graph depicting the automaton? Huh? Okay, so your colleague is wondering what I just said, and I said there is a set of final or accepting states, and this should be a subset of the collection of all states. Note the fact that this is a set means that the automaton can have 0, 1, or more accept states. It doesn't have to be have a single one. And in fact, we've already drawn an automaton which has more than one accept state. We don't need to remember it. I think we can just put it up. This one had 2 accept states, S0 and S1. We've also drawn an automaton that has no accept states whatsoever. This one. So the set of accept states can be empty. But in all cases, the accept states are states. So the set of accept states is a subset of the set of all states. Keep asking questions. If I can, I will answer. So far so good, but that's boring. What breathes life into the automaton is what the automaton does when it is in a given state and it reads some input symbol. So where is this described? This is described by means of the transition function. Now, this is a function that takes 2 inputs and returns 1 output. Now, what are the inputs? The inputs are a state, namely the state where the automaton is currently residing, and the next input symbol that the automaton reads. Based on these 2 bits of information, where the automaton is and what it reads, the automaton will change state to a possibly new state. And that's the output that is returned by the transition function. Pictorially, we always draw this function as a graph, as an edge, in terms of edges in a graph, whose nodes are the states of the automaton. And these edges are labeled by the input symbol that has to be read in order for the edge to be followed. Okay, so you can think of this transition function as a table that tells you, as a 2-dimensional table that tells you, given the state that you're in and given what you read, this is where you go. Now, why is this automaton deterministic? Okay, what does deterministic mean to begin with? Deterministic means that the machine, when it is fed with an input string, it will always do exactly one thing. Given a state that you're currently in and given a symbol that you read, there is exactly one and only one possible next state. The opposite of this is non-determinism, where the machine actually chooses possibly to go in one or many different places. And we will see in the future lectures, actually, a version of machines which are non-deterministic, that have the power of magic in a strong sense. Okay, the fact that this is a deterministic automaton is embedded in this word that I'm using here. It's a function. A function says, okay, give me an input, I'll give you one output. And exactly one, and always the same one. I've already answered the last question. An automaton can have an empty set of states. In fact, we already drew one that had no states whatsoever. But let me ask you the second question. Can a DFA have an empty set of states? Can S, capital S, be empty? No, of course not. Why not? Because of the start state. There has to be a start state. And the start state is always a state. Okay? So, you know, in this definition, there is everything that you need to know in order to determine whether an object that somebody shows you is a finite automaton or not. It's a finite automaton if it obeys all these constraints. The set of states should be finite. The input alphabet should be finite. The transition function should be deterministic, blah, 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 and all the rest. Okay, so now we know what an automaton is like, and we could actually go and define formally how the automaton operates on a string. There is a whole slide on this, which I put for your reference. You don't need to read it now. You can read it at home. Otherwise, you get scared. But we've already, this essentially formalizes what we've done in pictures, which will be sufficient for you to operate on automata. Now, the only thing I want you to focus on is the language which is accepted by an automaton. So somebody gives you an automaton and says, and asks you, what is the language accepted by this automaton? Well, formally, the language accepted by that automaton is the collection of all strings over the input alphabet, such that the automaton, by processing that input string to completion, starting from the start state, lands in an accept state at the end. Okay, so a string is accepted by an automaton if the automaton starts reading the input string one step at a time, one symbol at a time, follows the transition function along the way in processing the string, and once it has finished reading the string, it will have reached perhaps here. We'll look at the state that it is in. If it's an accept state, it will say, yes, I accept it. If it's not an accept state, it will say no. I'm going this way because I go from left to right. Otherwise, I will go on that way. Okay? So that's really the definition. So let me give you a little test here. Let's do reverse engineering. Now I give you an automaton, and I want you to tell me in English what is the language accepted by that automaton. You can also do it in mathematics if you wish. Okay, so what is the language accepted by this automaton? Sorry, say it again. The language containing A and B, absolutely, but any string that you can build using A's and B's, including the empty string. So the language accepted by this automaton is AB star. Because that's the set of all strings that you can write using A and B. Now, why is that the case? Well, this automaton accepts, well, no matter what it reads, it stays in the start state. At the end, it will be always in the start state because that's the only state. That's a happy state, so it can never be unhappy. It always says, give me an input, I'll be fine with it. So I accept everything. Excellent. Let me give you another, perhaps slightly more complicated example. What does this automaton accept? What strings will make this automaton happy?
A and
Okay, your colleague, so anybody? Yeah, somebody at the back. Let's give precedence to the back. I mean, it doesn't matter if you get it right or wrong. I mean, we're here. Okay, your colleague in the front row, inspired by your colleague in the back row and your colleague in the third row, said all the strings of A's and B's that contain an odd number of A's. And that's right. Let's see why. Let's try to understand what these states actually mean. This one means I've seen an even number of A's. And this state here means I've seen an odd number of A's. And the behavior of the automaton actually reinforces this intuitive viewpoint. Why? You start processing your string, your input string, in your start state. If you see B's, your start state means I've seen an even number of A's. If you see B's, the number of A's you've seen is still even. It was even before. You only see B's, it stays even, the number of A's. Even means that you can divide it by 2. So you've seen 0, 2, 4, 6 number of A's. Now, if you see an A, and you were in a state that meant I've seen before only an even number of A's, where you've seen one more, the number of A's becomes odd. And you get to an accept state. So you're happy. If you now see B's, you stay happy because you had seen an odd number of A's. The fact that you're seeing B's doesn't change that. But if you see another A, then you were odd before, the parity of the number of A's changes, you become even again. And that's not a happy state. That's why this automaton accepts all the strings of A's and B's with an odd number of A's. So let's write it for those who are at home on YouTube and anyway have done this exercise themselves without listening to us. I'm sure it's true. It's the set of all strings of A's and B's such that W as an, that's an S, as an odd number of A's. Are you satisfied? Happy with that? Thank you very much to the guys who contributed to the solution of this little riddle. And I said guys because it so happened they were guys. Ladies, come on, it's your turn now. Don't be afraid. I haven't had lunch yet, but I usually don't bite. Yes. Sorry, say it again. The language that consists of all the strings of A's and B's that contain string W, such that W has an odd number of A's. So I'm writing it in natural language. Yes. The question is it okay to write it like this? Yes, it is okay. It says, you know, mathematicians use natural language most of the time. So you would be surprised. The important thing is that what you write is something that anybody else but you can understand. If you're the only one who can understand it, then rewrite it. You know what happens is that if today you're the only one who can understand it, tomorrow even you will not be able to understand it. It happens to me all the time. And I'm not the only one, I think. Okay, so we've seen examples. Now, let me make you do one more programming exercise. Then the rest you will do at your leisure. Usually on the slides, there are going to be lots of questions so that you can practice at home or whenever you have time. And get your friends to practice with you. In fact, you can explain to them finite automata over a beer. You will be very popular. So let's look at the last one. The last one will involve a little bit more of programming than we've done so far, but why not? Sooner or later, we need to do a little bit of write a longer program than we've done before. So I would be interested in you coming up with a finite automaton that accepts strings of A's and B's, but it should only accept those strings that somewhere in them have the string A, B, B as a substring. Okay? So let's do it. I want to use this other one. So I want strings that contain the pattern A, B, B. So there could be something before, something afterwards. These are all the strings that I'm interested in. Now, you know, this could be the name of a file. You, at some point in your life, wrote a file name with ABB in it, and you want to look, you're at the command prompt, and you want to find all the file names in your current directory that actually, in their name, have the string ABB. Have you ever tried to do that? I'm sure, well, no, okay, you will. Perhaps not with ABB as a substring, but with something like assignment 1. Or something more meaningful than that. Okay? So, you know who does this job? It's actually a finite automaton. You just don't see it. So, your job is to make it visible. So this is my initial state, and now I'm waiting for your input. In the initial state, I haven't seen anything of my input string. And now the first input comes along, and it could either be an A or a B. Let's assume it's an A. Do you think I should stay in the same state, or the fact that I've seen an A tells me that maybe I've started seeing the beginning of something useful? You go to a new state. Why? Because this A could actually be the beginning of the pattern I'm looking for. So I go somewhere else. Okay, so let's continue. Then we see what happens when you see a B. Okay, if you see a B instead, what do? You can loop, because it means I'm still waiting for the possible beginning of my input pattern, or the pattern I want to check for. So now I'm in this state. If I see an A, where do I go? Okay, there are two possible suggestions here. One of them is loop, the other one is go back. I would say we loop. Why? Because this state actually means I've seen an A, whereas the initial state means I haven't yet seen anything of the pattern I'm looking for. And if you see an A, then you have seen possibly the first character in the pattern you're looking for. So there should be a loop here. That's the meaningful thing. And this state means I last saw an A. Okay? So what if you see a B? You go to another state, because this B actually could be the second letter in the pattern I'm looking for. Okay, this state means, let me write AB inside, because it means I last saw AB. The last two things I saw were an A followed by a B. Okay? What happens now if I see a B in this state? Okay, you have to leave this state, because if you see a B, the last two symbols you've seen are BB, Brigitte Bardot for people from my generation, but not AB. But if you see a B, this screws up completely the pattern that you were looking for, so you need to start looking again. So you go back to the initial state. What happens if instead you see an A? You go to a new state, because now you've seen ABA, or your input string of the pattern you're looking for. If you get here, you've seen an A followed by a B followed by an A. And this is 3 of the 5 symbols that you want to see. Okay, now you know what I'm about to ask. From this state, you have to decide what to do if you see an A or a B. Okay, so what if you see an A? You go back to the second state, which corresponds to I saw an A last. Okay, what if you see a B? You go to another state, because now you want to remember I've seen A, B, A, B. And now you know what I'm about to ask. What do you do from this state if you see an A? Okay, so if you see an A, you go to ABA. Because if you see an A, then the useful part of the pattern that you've seen is ABA last. And if you see a B, where do you go? To a new state where you've seen your pattern. So you are happy. And you stay happy ever after. Okay, double circle. This guy used to have 2 ears, but ISIS cut one of his ears. Okay? So you program a finite automaton that recognizes the pattern. So this finite automaton actually is the guy who would do the job when you do, if you're using Linux, ls star followed by a b b star. Question? Okay, so if you are in this state and you get as input A, the last thing you will have seen are 2 A's in a row. You see, yeah, at that point, the only useful thing of the pattern is that you last saw an A. That's why you go back to the second state in the row. Now, this already looks like a fair amount of programming. But you know what? The good thing is that you don't need to do it yourself. There is an algorithm for constructing this finite automaton from the pattern that you actually want to search for. That's something that we might call the grep problem. By the way, have you ever used grep?
I did it. It's a part of like command line.
It's a part of command line Linux. How does it work? So what does it do? If you do grep,
It sorts things, right?
now grep doesn't sort things. So if you do grep pattern file, the result would be all the lines in your input file where the pattern that you're looking for occurs. So for instance, if you did grep pattern ABB, that's the one we were looking for before with our finite automaton in input file, and this input file could be the list of all the file names in your current directory, then this will return all the file names in your input, in your current directory, that have a name that matches that pattern, in this case, that have A, B, in them. So this is an algorithmic problem that you just solved for me in a specific setting. But this is the general formulation, and we will solve it. We will see how this can be solved. At least I will show you that this has been solved. You use it anyway every day, so you know that it has been solved. But this is just by way of motivation for finite automata, one of the many motivations for finite automata. The algorithmic problem has as input a text, which is sort of the content of a file, of some length t. And it has a string w of some length n, which is the pattern you're looking for. And the problem you want to solve is, at the very least, you want to know whether w appears in the text t. Now, typically, the pattern is short, the text is humongously long. For instance, the text could be the human genome, my genome, your genome. And the pattern could be some sequence of genes that will make sure that I go crazy tomorrow. And solving this problem is just to figure out whether I should actually get worried today. Do I have this sequence of genes in my genome that exposes me to a high chance of becoming crazy tomorrow? So this is not just useful in text searching, it's useful in many scenarios, not least in bioinformatics and modern biology. How do you solve this? Finite automata to the rescue. And this is sort of a trailer for Tuesday. Any questions? So that I don't get told today that the lecture should be over in 2 minutes. Okay, if there are no questions, the lecture is over now. Thank you.